The topic for today, oh, we got somebody post the chat. Hello all. Hello. The topic for today is reinforcement learning, which is how you get a machine to plan for the future when it only gets a reward at the end, right? So suppose it's playing Go or making a pina colada, it gets the reward at the end, and it has to decide what steps to take early in the game. So I just grabbed here some of the applications that we'll talk more about in the ethics thing, but today we're talking about how to do image processing, how to do speech recognition, and then oh, there's more, but we'll talk about them later. So for convolution nets, we might be looking for, is it a cat? And you'll note that the cat may be located many places in your image, and no matter where it is, you want to be able to say it's a cat. And if the cat has different sizes, or you rotate the cats differently, then it's still a cat. And you know, we want to have an internal image of what a cat looks like, and be able to use that same information to recognize it no matter where it's located. It's not like we have a part of our brain that says if a cat's here, then we recognize it, in a separate part of our brain that recognizes a cat somewhere else. Our learning is invariant to location. So convolution nets learn invariant over space, and recurrent nets, which we are used more for sort of sound, right? If I say hello here, if I say hello here in time, then you should be able to recognize the word hello. So recurrent nets are invariant in time. Jeff Hinton, who's the big guy in machine learning and is at U of T, he was there when I was a graduate student. He came up to York and gave us a talk on how the new thinking is to have a three-dimensional model for the cat and be able to be invariant on which rotations you see. The way it is now, if you see this image of a cat and this image of a cat, you have to learn it completely separately because it doesn't have a way of rotating the image. But we're not going to talk about that today because it's not done in practice and I don't know it that well. But we're going to talk about moving rotations in space. All right, so here's your neural net, and what we kind of talked about before is it's layered like this, and between every node at one layer and every node at another layer, there's a separate edge with a separate weight. So that's called a dense layer, and but we might want fewer weights, or we might want to put some constraints on those weights. Why? We might want to decrease our computing time. We want to decrease how much overfitting that it can. Remember, overfitting is when you can memorize anything because you have too powerful of a machine. And so we can add some constraints on these weights. So the one thing is we could do is we could say these two weights have to, for some reason, have to have the same value. Or we could say, hey, this edge is always is just not there. Or it's like we constrain it to have a weight of 0. So how would we do sort of space convolutions, space invariance? Is, well, here's an image of a bicycle that we want to recognize, and there's the pixels up at the top of the image are going to that node, and the pixels sort of at the bottom of the image are going to this node, and then there's some hidden node in here which is supposed to say hey, is there some, I'm looking for some feature, maybe a cat, or maybe some smaller feature like an edge. And I can ask, hey, is that feature in the top of my image? And I could have a different node that says the same feature, does it appear in the bottom of the graph of the image, right? So both of these features, both of these hidden nodes are going to fire when they find a feature, the same feature. They're looking for the same feature, but in different locations, right? So here, as we do the learning, it learns the weights on the edges so that it can find the features at the top here. And so since it's learning the same feature, why don't we just force the weights to be the same, right? Because you're learning, whatever you're learning up here to try to find, is this a cat up here? Well, you might as well use the same weights on these edges so that you're learning, parallel learning, is the cat there or is it there, right? And similarly, these cross edges, well, they might as well be forced to 0. Why? Because whether there's a cat down here, is there a cat down here in the graph, doesn't need to know the pixels about the pixels at the top of the image, right? If you're looking for a cat down here in the image, you don't look at pixels up there in the image. So these cross weights, edges just won't be there, right? And people study the brain when they try to think about how to build neural nets. And the brain takes the image where it's sort of pixels, whether it's firing in your eyes and in the receptive field, and then has a set of axons at the first level that somehow look for features, like they're edge detectors, and there's is it changing? I don't know, various detectors. So that's what we're going to have here. We're going to have layers in our neural net, and the first layer is just pixels, and then the next layer is going to be looking for edges. What's an edge? Is where it's going from black to white, or from white to black. That's an edge. And then the next layer might be looking for combining these edges into more complex features, right? And then the next layer might be combining those right here. That there might be down here a nose detector and an eye detector. And then up at this level, it combines a face detector based on whether does it have a nose and does it have an eye, right? So that's kind of how it works. However, remember I told you these hidden nodes, we were never going to actually talk about noses. That's what I said in the first talk, and here I am talking about noses. But these weights in here, these images little images that are features that it's looking for, aren't put in there by a human. They're all, it's all learned by gradient descent, right? I stole this image from the internet, so I don't absolutely know what it's doing. Whether it's just it could be just a conceptual thing that they're saying might happen at the various levels. But I do know that they also, after they build a neural net, then they sometimes ask, right, what is being looked at here and what's being looked at here? And so maybe these are actual things that various features are being learned within the neural net. I don't know. All right. But let's focus on a particular feature and think about how it's detected. All right. So before we go on, let's just have a reminder of what we did in the algebra talk. Right. In the algebra talk, we were trying to do thinking about setting up a dating service. where here are two people with their various features, and we can think about their list of numbers as being a vector, right? So W is this list of numbers, and X is this list of numbers. And the way we find out are these two people compatible is we kind of measure the correlation between how these vectors are similar. And that's done by taking a dot product. Remember, a dot product multiplies these two numbers and multiplies these two numbers. In each coordinate, it multiplies the pair of numbers, and then it adds it all up. And that tells us whether they're correlated or not, the dot product. And you might remember I also showed you this image, that if you have the two vectors, that the dot product is kind of related to the length of, if you project one on the other, it's related to the cosine between them. For example, the dot product is 0 when it's 90 degrees and is 1 when the two vectors are the same. And it's also related to projecting one vector on the other. So it's sort of saying how much these two vectors are similar to each other. And so you can have one of these vectors could be saying, this is what I'm looking for, right? The weights here is a vector that says, I'm looking for vectors that look like this. And then the purple one are the pixels that are there. And you take the product and it says, hey, do these pixels line up and look like the pattern we're looking for? All right. So let's see how that works here. Here in the back image is the back matrix here is the entire image with all their pixels, right? And this little square is just looking for a feature, right? I don't know how big their features are in general, but here's just a 3 by 3 feature. Maybe it's looking for just a teeny little line. And so that the weights, these numbers in this little square here are the weights of the feature. So what I guess you can sort of see, if this is a 2 and a 2, it's wanting 2s here, it's not wanting, wherever it has a negative number, it's saying I don't want that. And whenever it has a positive number, it's saying I do want that. Whenever it has a 0, I say I don't care what's there. So it tries to find out, it records right here one number, which tells me, does this pattern appear right there in the image? And the way it does it is it takes a dot product, a linear combination of the pixels here and the filter. They're calling it a filter. Right? So basically it's taking this number times this number plus this number times this number plus this number times this number, right? And that gives you one number, and that number will be big if the pattern sort of appears here, right? If this pattern is what looks at here, and it will be, if it's just random noise here compared to the pattern, then you would get something more like 0. And you might get something negative here if it's the opposite of what you're looking for, right? Does that make sense? So how does that work now is down here we have a really big image, and you can see it's looking for a 3 by 3 filter. So there's one weights of a 3 by 3 filter, and that same filter is getting applied, right? You learn the 9 weights for that filter, and then you apply the exact same 9 weight filter all through the image. And you can see at what are we getting in the top matrix is we're getting, for every location of where the filter might be, we're getting one number, right? So this number says, does the image from the filter, does the feature appear here? And then we say, does it appear here? Does it appear here? Does it appear here? Right? So this becomes a matrix which tells you where the feature appears within your entire image, right? Does that make sense?
It looks to me like it's scanning, right? It's a scanning process.
Yeah, so it's all happening in parallel at the same time.
Yeah.
So there's not really a sense of it's happening in time, it's happening in parallel, but you're right. Right, so, and the advantage of this is to go from all of these huge image to this reporting of the feature only requires learning 9 weights, right? They're the 9 weights of the feature, and then this tells us where do the feature, which is specified by the 9 weights, where does it appear in the image? All right. So, right, and so this matrix that we produce tells you where that feature appears. All right. So now in our neural net, we might start. They're layers, and at the bottom layer we have the input, and then we have many feature maps. Remember, we described how to get one of these feature maps. Maybe this feature map is dictated by a 9 by 9 matrix of weights, and those weights are moved all through the image to give you this mapping, which tells you where does that feature appear in the image. But then each of these, see, there are many of them, because we'll learn many features, and each of the features were being looked at in this thing here, right? So here, I guess, back to this image, right? Here are lots of different features, and for each of these features, we could say, where does this feature appear in the image? Where does this feature appear in the image? And that's what, for each of these are little filters probably, and for each of them, we will get a matrix like this saying where that feature appears in the image. All right. And then after we do that, then they sometimes have what's called a pooling layer. And what a pooling layer says is, remember this number here says, does the feature appear here? Does it appear here? Does it appear here? Does it appear here? And what they might do is they might take those 4 values and take the maximum of it, right? So the 6 is the maximum pink value, and the 8's the maximum green value, and so forth. And why do they do that is because now it's the 6 tells me, does the feature appear anywhere here, right? I don't care exactly where it is. I just want to know somewhere in this region, does there appear a feature? And you'll see the advantage of it is it divided the number of numbers we have by 4, right? So that's the goal is to bring it down to one number, which says, is this an image of a cat or a face? And so we got to have fewer and fewer numbers, and this is one way of getting fewer numbers, right? So we can say, hey, is the nose somewhere in here? This says, is the nose here, 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 or here? And this says, does the nose appear somewhere in there, right? So then that's what we have. We have the pixels, and then we have lots of learned features, and we ask where those features are, and then we do a pooling. And then they might have another layer of doing learning convolutions, right? Each of these convolutions would probably be on one of these features. And then at some point near the top, they'll do linear classifiers where you take sums and thresholds. And in the end, you learn out whether it's a face or a dog or something, right? Are people kind of following that?
Mm-hmm.
All right. Now, you might say, well, this is a much more complicated machine. How do we possibly learn this? And I'm saying it's learned exactly the same as we did before, right? The neural net, this big neural net, is just something that what it does depends on weights. And the only difference is some of the weights are used repeatedly in different places. That doesn't matter, it's still a weight. And maybe some of the weights are fixed to 0, that doesn't matter. And maybe some of the other functions are maximums, but that doesn't really change what we're doing here. How do we learn? Just as before, we have our current weights, and given our current weights, we calculate the error of how well it does. And for every possible setting of the weights, we get an error, and that gives you an error surface. And then you use gradient descent to find the weights that minimizes the error of this machine, right? So basically, if you wrote a code that does gradient descent for the type of machines we had before, you don't have to do anything different. Maybe you might have to take slightly different derivatives as you pass through maximums and stuff, but it's the same idea, right? Does that make sense? So now let's do the exact same thing for time. That was an invariant over space, but when there's variant over time, it's called a convolution net. Convolution is a math concept which has to do with that. We won't get into it. Recurrent nets have to do with time. Something's recurring through time, right? So here we have some voice that they're trying to, speech that you're trying to recognize, that you're saying hello world, and it moves through time. So here these inputs might be asking what time happens at this point in time, and then these neurons here are taking in what happens later in time, and maybe here we're looking for some feature like the word hello early in time, and here we're looking for some feature in time like hello later in time, right? And so again, we can learn using the same weights, right? Because it doesn't matter whether the hello was early in time or late in time, you're going to use the same sort of methods for learning it. So what might our architecture look like? Well, you could do some sort of convolution net like we did before, and more or less that's kind of what we're doing here. But we're going to add some extra little features here. All right, so here's our this down here is the speech. Say English speech. Somebody's talking in English, and it's getting fed into our neural net here, and then what it's going to output is this more speech, but it's going to be in French. All right, so this is the little, like we saw in Star Trek, or the little fish that's in your ear that takes in English speech and outputs French speech, right? And their neural nets this time is going to have cycles in it. So all our neural nets before were layered, so there was never a path that went around in a circle. But we're going to, since it's sort of time, we're going to have these cycles in the neurons. All right. And one way to understand it better, even though it's reusing as you go around and around in time, it's reusing the same weights, right? Because that's whether you say hello near the beginning or you say hello near the end. That hello later is going to cycle around and use the same weights. All right. So, but we can imagine, we can unfold this into different time slices, and we can see what's happening, right? So here's a particular point in time, and the machine is remembering something about the past, right? How I recognize the next word in my sentence depends on what I've heard in the past. So it's remembering something about the past. Maybe it's remembering based on the grammar so far, is the next word, is it likely to be a noun? Is it likely to be a verb? What types of things, right? You certainly know there's predictive text where you've seen text so far and it tries to, based on what you've seen so far, predict what the next word's going to be, right? So that's some information here telling us what we remember about the past, right? And then what gets fed in is the next bit, the next word, say, or the next bit of the speech gets fed in here into time. So now we're going to combine what we know about the past and the new word that's coming in, and we're going to pass it through some neural net, which is then going to give some output, right? And that output might be, right, this might be the next English word, and this might be the next French word, right? And then we're going to move forward through time. So what it's going to pass forward, what actually in some ways is wrapping around here, what gets passed forward is what it's remembered about the past, right? Here's the old past, here's the new word, and then it combines those to give us what does it remember about the past now, because we have now later in time, right? And then a next moment in time message comes in, and it outputs the next message, and it remembers something about the past, right? And then the next English word comes in, it outputs the next French word, and it remembers something about the past. And that's kind of how it goes along. Does that kind of make sense?
Yeah, it's like patterns, right? It's like a series of patterns that it's recognizing.
Exactly. Now we can make this machine even more complex. This doesn't have any long-term memory, right? It just has short-term memory. It remembers one vector of information about what it's passing along, right? But it might want to differentiate between things that it remembers from the immediate past versus things that it remembers from the far, far past.
Right.
So in order to talk about memory, I grabbed some slides from a whole different course that's talking about memory. And how does memory work? Well, it's a bunch of registers that's outputting some value that's stored, right? This value is stored in memory, and it's outputting that value. And normally there's a clock, but I just changed this clock into a lock. And when the lock is low, it's going to remember the value. And see, there are different time periods. It might remember that for a long, long time. It might remember some value. But then when the lock goes high, here the lock comes high, then some new value, right? We were learning the old value, and when the lock comes high, we learn some new value, right? And it's not hard to build such memory out of AND gates and OR gates. And here just you could work that out if you want, how it remembers. But you'll note there's a little cycle in here. The cycle says, what do I want to remember? You know, it feeds back what I want to remember back into the register. Anyway, how does that relate to what we're doing here? Well, everything is learned by weights, but the weights could dictate, hey, if this kind of thing is happening, then I want to open the lock and store some bit of information. And then later on, the weights might say, hey, based on what is happening now, right? And as long as those values are in there, right, it stores some value. As long as that value is in there, it can reference the information that's stored. But maybe when it reads a period in the sentence, it says, hey, this is a new sentence. So let's lower the lock and store new information. We're starting something new, right? So that is all learned by the neural net, when to open and close these locks, and when to store stuff, and when to have what to remember from the past. It's all learned by gradient descent, right? So how does this work? Just as before, right, we're doing supervised learning. So there's lots of data which says if this is the English input, then this should be the French output. And the supervisor provides the output, and then it computes some error of the difference between what is outputted and what should be outputted. And then there's just the machine is defined by all these weights. And just like, right? And these, what's the difference is, well, again, the weights may be the same, right? If it has little cycles, maybe the weights are appearing in some cycles, or maybe some weights are 0, or, but at any rate, how do you learn all the weights? You do gradient descent, right? Are people following this? Any questions about this topic? Because it's sort of, we're going on to a new topic now. How you doing, Martin? I can't hear you, Martin, but.
Is he there?
Yeah. Oh, Jake's, that was Jake.
There we go.
Hey, Martin.
Trying to think with the cycles there, the end result, it may never be fixed. Like it might never stop, doesn't it?
Yeah, so I think these cycles happen in step, right? So in some ways, this X here is misleading because it doesn't come all in at once. It has fixed weights, but then at one time this comes in, and then things cycle around, and then this comes in and this cycles around. I think conceptually it's much better to think this is your neural net here. It doesn't have cycles. It all the input comes and it computes, right? But so in some ways the information here goes all the way along here and moves along, right? So if you unwind this you can think about this neural net with cycles is being unwound for some number of time steps, and you'd probably unwind it for the length of time that your input's coming, right? Or you might, maybe it needs to, or at least it's going to unwind for the length of time that output is being produced. So right. I think conception, in terms of thinking about the machine, you think about it as the unwound machine, right? And then it doesn't have any weights. I mean, sorry, and then it doesn't have any cycles, right? Right. And so it's just learning, given the input output pairs, right? How do you learn those weights, right? But in reality, this might be a lot of time, and so this, the same weights get learned over and over again. So in reality, the weights are only stored one place, right? But when you put in an image, the way you compute, or when you put in some input here, which is English speech, right? It goes around and around and around and around, and then out as you goes around, it outputs stuff, right?
So Jeff, question for you.
Yeah.
In the supervised, yes. Can I? I'm speaking now. If the training is taking place with, I would imagine, translators that are giving French speech correctly, right, versus the English speech that's coming in, but there's still going to be variability between translator A versus translator B and translator C.
Sure.
Well, yeah.
Sure. For sure. And then the problem where in French the word order is different than it is in English. I mean, there's just so many layers of problems here, right? I just only understand the most superficial level of this. I mean, one of the problems of me teaching you everything I know is that if you have questions, then I don't have the answers for them.
No problem. This is a very entertaining and educational, right? Even then. Right,
for sure. These are very hard problems, and it's been taking over the years. The speech recognition has gotten better and better. So who knows what they're doing to make that happen. But I think the underlying principles here are the same.
Mhm.
And certainly at the beginning, you know, I don't know, 10 years ago, 20 years ago, you know, when you want to do speech recognition, you had to train it on your own voice. Any other thoughts about those recurrent nets? So the next topic is when you don't have rewards until later. You're playing sort of a game and you don't have rewards until the end, right? So driving, you have to do a lot of steering and thinking and braking before you get a reward of did you get where you wanted to go or did you hit the person walking, right? And robots have to do a lot of planning. And certainly the classic is games. And you know, back in here, I guess back in our past, it was pretty exciting when Big Blue, Deep Blue won chess, and then they won at Jeopardy, and nobody was expecting them to win at Go for a long, long time. And it's fun to watch the movie in which they you watch this poor guy lose. Nobody expected him to lose, and in fact, it was even the machine learning people didn't expect it to win. And this was all trained by having the neural net watch how humans play. And then 2 years later, they threw all that away and they started over again. And they had the neural nets, just no human interaction. They just played lots and lots of games with itself. And it learned how to play in a way that then just beats everybody, right? This neural net just knows how to play Go, right? And then later, people got excited when it learned how to play video games, which seemed to me to be easier than this, but it's harder because it's all real-time interactions. And I understand the next big game to play is to learn how to play cooperative games. But right now, you feed the rules of a game. You take any game, you feed the rules into, and it will learn to beat you. I guess the one thing that neural nets aren't good at doing is if you teach it how to play one game and then you give it a game which is very similar, it can't move what it's learned about one game onto another game. It has to start fresh and learn the new game. But anyway, let's think about games. And probably the way to start is with game trees. You know, you've heard about machines doing look ahead 4 or 5 levels of the game tree. So this is what I mean by a game tree. And what is it? Each node here is some state, the state of the game. And when I'm in this state, since it has a white circle and the white guy inside, it's the white's move, and the white gets to choose how to move. And then based on which move, this says the white then chose to go this way. So now we're in this state. And in this state, it's the black's turn. And black has a number of different ways to move. And black chose to go this way. And then it's white's turn. And white gets to choose. White chose that way. Everybody's choosing the leftmost choice. I'm not sure why. But here, this guy, he chooses to go this way. And then we get down to a star. And if it's a black star, then black wins. And if it's a white star, white wins, right? So this tree then defines the game. And each person has to figure out which move to make in order to win, right? So the best way to figure out who has a winning strategy is to work backwards, all right? We start at the leaves, and just about an hour or two ago, these slides are freshly made. I stuck in those purple numbers, and those purple numbers tell you the reward at the end of the game. All right, so R for reward. And here I'm making it with respect to the black player. I could have done it with respect to the white player. So you see, you might notice that whenever it's the black star, that's because black wins, then it's a positive number because black is very positive about winning. And whenever it's a white star, it's a negative number because black is pretty negative on losing, right? Pretty negative on white winning. So, but here we're in the stars, we're just saying winning or losing, but I'm expanding it to how much did you win by? Did I win by a lot or a little bit? And so here -6 means white wins by a lot, while +6 means that black wins by a lot, right? And so we can label, this is the end of the game, right? So we can label the end state based on rewarding them for how well they played the game, right? And now suppose that we're in this state and it's black's turn to go, right? So black gets to decide which move to make, and black gets to decide, do I move towards the -3 in which I lose? Do I move towards the 2 in which I win, but I only win by 2? Or do I go this way in which I win by 4? And right, what he does is he just goes the direction that's going to maximize. He looks at these numbers and he moves in the direction that maximizes his win. All right. So here I'm just adding what I've just computed for each of these what the maximum is, right? The maximum of 5, -2, 3 is 5, right? The maximum of these is 3. Now these numbers are all negative, so the maximum is -2, right? And so these numbers tell you how well black will do when in that state, right? Because if he was in this state, then he expects to win by 4 because, you know, he's going to follow the path down to 4. So that's how much he expects to win here, right? And then we can roll back and we say, what happens if we're in this state? Well, in this state, the white player can look down at each. If he comes down to this move, he says, oh, it's 4. I'm going to lose by 4. Here I'm going to win by 3. Here I'm going to lose by 2. So which one does he take? He comes down to the one where he wins. So what we do, he moves in the direction that minimizes this number, right? Black was maximizing his number and he's minimizing his number. So the minimum of these 3 numbers is the -3. And so these numbers now tell you how much, when in this state, black is going to win by -2, right? Sorry, black is going to win. How much is black going to win by? -3, which means he's going to lose, right? In this state, he's going to lose because white's going to go this way, which is all white, right? So while in this, right here, the max white's in this state, black's going to win. Why? Because it doesn't matter. Oh, look, it looks like I took the maximum. In this case, I took the minimum wrong, right? That should be a -3, right? So ignore that 6. It's really a -3. All right. And that mistake is going to trickle up. So now the black takes the maximum again, right? He's going to take the maximum is the -2. Here we took the maximum is the 6, which shouldn't really be a 6. And then we take the minimum again, right? We take layers of max min, right? Does that make sense? And at the top here, the number at the top is -2, which tells us that white has a winning strategy, right? And how would the game play is, well, whenever it's white's turn, he makes the move that moves to the minimum choice. And whenever it's black's move, he takes the move to the maximum choice. And it will come down to, you follow the path, it will move down to this -2 where white wins. Everybody follow game trees?
I have a question.
Yeah.
just curious, like, the idea wouldn't be that the possibility of a game tree exists already. It's being constructed as the game is played. Yes.
Yeah. So the problem with game trees is you see they grow exponentially, and if you did the game tree, right, if you're playing chess,
Yeah.
right, there may be 16 pieces, and each piece has a number of places to move, right? So maybe there are 30 moves you can make. So there are 30 nodes at that tree, and 30 squared at the next, and 30 cubed at the next, right? So this game tree grows hugely fast, and unless it's a simple game, you just can't play it out very deep. All right. So let's talk about Markoff chains. They're also a cool thing in mathematics that everybody should know. It's right, a Markoff chain has states, and it puts probabilities between the states, right? So if I'm sleeping, then with probability 20%, I stay sleeping, and with probability 20%, I eat ice cream, and with probability 60%, I run, right? And so then our little robot is just going to move around according to this Markoff chain. And what's true about the definition of a Markoff chain is that what happens next only depends on the state, your current state. It doesn't depend on anything further past than the state you're currently in. And there are lots of theorems about, and you can form matrices of these probabilities, and you can solve the equations to find out what percentage of the time you're in each state, right? I expect to be sleeping, what percentage of the time I expect to be running, right? That's your sort of steady state, is what fraction you're in each of these states. But it's a good principle to know, right? It's, again, we're moving from state to state, and we're doing it randomly. All right, but now reinforcement learning is, well, we don't want to be moving randomly, right? We want to be learning and making decisions, and at the end, after it travels a lot, then what does the robot want to be rewarded with? It wants to be rewarded by eating ice cream. It doesn't want to be flipping back between sleeping and running, right? It wants to be eating ice cream. So that's when it gets rewarded, right? So what are the uses of reinforcement learning? I guess I already told you about AlphaGo, but it's basically, it's when the reward for what you're doing now doesn't come until much later, right? You can run and eat ice cream, run and sleep, but then when you get rewarded is when you get to the ice cream. All right, so we can do this exactly, it's like through time as we did before, right? We could say there's a current thing that it remembers about the board. What does it remember? It remembers the placement of the current placement about the pieces. That's what it remembers, right? And then some input comes, which might say, what did your opponent do, right? And then it calculates some output, which might be, what move should I take now, right? And then it knows what the current board again is, right? Because your opponent made a move, you made a move, and now we have a new board, right? And then we learn what your opponent does, we learn what you figure out what you're gonna do, and then there's a new board, right? And we keep moving through there. So this is just what we did before, right? Everybody buying this? Right? And again, you can think about this as a machine with cycles that's going through time, right? I'm in some state and I get some input from the world, I go into a new state, right? And then I get some input from the world, I make some decision, I go into a new state. And so it kind of, we can go back to Markov's, right? And then just say it again, right? You don't learn whether you win or you lose until the end, right? So you have to somehow back propagate that information all the way back, right? the fact that you got an error at the end, you need to you use forward propagation to figure out what the machine does. And then that, taking the derivatives, does back propagation all the way back to say, how do I change what I did really at the beginning in order to affect the error at the end, right? So, so now, if people are ready to go on, this F is stating, what do I remember about the world, right? It's where are all the pieces on the board? It somehow is telling me my current state, right? And so we're going to form a graph just like we did with the Markoff chains, and each state is going to, each value of F will be a different state, right? I'm in this state, then I'm in this state, then I'm in this state. That's told by the values coming out of here, all right? So, and maybe I'm in some state here, right? Here I'm eating ice cream and some input comes in, and then I'm over here, I'm sleeping, and then something happens, and now I'm in another state, I'm running. So you're moving from state to state. And so that's what we're trying to learn of how to move from state to state. And so we're going to represent it by this graph where here my these values here tell me that I'm eating ice cream, and then something happens, and then I'm in the state here where I'm sleeping, right? Does that make sense? And our machine is going to move from one state to another, right? So here he is, our machine moving from different states. And so here's my little piece of graph that we're going to work on. And the robot's going to move through these states. And each of these, right, we could call it a node of your graph, or you could call it the state that the machine is, right? The machine at each point is located somewhere, right? And we're going to label each node with the value, I guess on the other page it was F, but we're switching over to U. I don't know why. But U is going to be everything that we know about the world, right? We're going to label, this is a fixed labeling, being in this state. What does it mean to be in this state? It means that what you know about the world is you. And if you knew something different about the world, if what you knew about the world was the values U2, then you would be in this state. And you move from state to state as what you know about the world changes, right? Or the world does change, right? So for example, this U value could tell you the location of all the pieces. So when you're in here, the pieces are laid out one way. And when you move over to this state, the pieces are laid out some other way. And just, you know, our Go board has a lot of squares. And so there are an awful lot of states, right? This is more states than there are atoms in the universe, right? So we don't actually build this graph. But anyway, the labeling on this node isn't very big, right? The labeling just tells me where all the nodes, where all the pieces are on your board, right? Everybody understand these states? You can just think about it as the state says where all the pieces are, and each way of arranging each way that the pieces might be on the board will be a different state, or maybe the state tells you, right, I'm currently sleeping, or I'm currently running, or whatever. All right, so now, just as we did with the purple numbers that we're percolating through, we're going to have each state is going to be labeled with a reward. And it's not the reward that you get when you're in this state, because you don't get any reward until the end. But it's what reward do I expect to if I'm in this state, right? If you're in this state, you can say, oh, this feels like a really good state for me. I feel really happy because from this state, I really expect to do well in the future, right? So the R value is something that has to be learned, and it sort of will will tell the machine, or the machine's trying to learn from playing. You play many, many games, and over playing many, many games, it learns the R value of every state. It learns, if I'm in this state, do I feel like I'm going to win or do I feel like I'm going to lose? Right? Everybody gets that the U tells me where the pieces are, and the R value tells me, given that's where the pieces are, do I expect that I'm going to win or lose? And if so, by how much?
So
Right?
Jeff,
Yeah.
if I can try to understand this, the U is the current position. Let's say chess in this case. Let's just
Right.
pick chess. Is the current position of all the pieces on the board now.
Yeah.
And so then you'd have to dynamically generate the R1, R2, R3, R4, which would correspond to every possible move you could make right now to another state, which would be the moving of one piece if it's your turn.
No, it's not about all different moves. It's just about, given this position, if I play optimally, maybe there's some randomness in there, and my opponent plays optimally, maybe there's some randomness there. Maybe there's some information about, how, you have to know how I'm going to play, and you have to know how my opponent's going to play. But so it's a complicated calculation. But in the end, what the R is one number, just one real number, telling me how much do I expect to win by, given that I'm in this is where my pieces are.
But I'm thinking of it as a computer programmer. I'm trying to think of data structures that I would use to represent my current position, maybe an array that's filled in with the piece that's in a particular checkbox of the chessboard. But then I could move that one stock that's in position 3,
You're getting
5.
ahead of us though.
Oh, okay.
Let's just say this is some value that's going to be very hard to calculate. And let's not worry right now about where it comes from. I'm just defining what I want it to be.
Okay.
What I'm wanting it to be is U, as you say, is some data structure telling you where all your pieces are. And then there's some evaluation, which, given my pieces are here, R then tells me somehow, I don't know where I get this R from, but it tells me somehow what's the probability I'm going to win given I'm in this state. Right? And if you play chess, you must have some sense of that, right? If I put pieces down in a form where it's a game that people play, you'd be able to look at the board, right? Suppose two people are playing chess and you walk in the room. You look at the board, if you're a good player, you'll know who's winning, right? Just static. You look at the board, you know who's winning in some way. If you know how to read the board, I wouldn't know how to read the board, right? Does that make sense? All right. Now we're going to have 4 different types of nodes here, right? Of these states. And some of these nodes, these states, it's our machine's turn to go, right? And in some of them, it's our adversary's turn. In some of them, the universe is going to flip coins because maybe it's a probabilistic game, right? If we're playing Monopoly, then some dice need to be rolled. And then in some states, the game's over and we stop, right? So those are the 4 types of nodes that we need to be worrying about, right? And so let's talk about each of those types of nodes. All right, so if it's the player's turn, right, now it's the player has to decide which way to go. Suppose the R values were already computed by some magic, right? Some oracle came down and labeled each state with the probability that you're going to win if you're in that state, right? So now the white player is sitting here. He knows his R value, so he knows the probability he's going to win. And he has to decide which of these, each edge coming out is an action he could take, right? I could move this piece, I could move this piece, I could move this piece. And of course, if he took that action, it changes, right? The U's tell me where all the pieces are. And if I take this action, then it tells me where all the pieces are going to be after I do move that move piece, right? So you can imagine where all these edges are, right? Given this is where all the pieces are, I know which pieces I'm allowed to move, and I know which states I would get to if I made that move, right? So what is the player going to do? He's going to imagine taking this move and figuring out what does the board look like if I were to take that move, and he needs to evaluate how good is the board when it's in that state. So he looks at this R2 value, and then he comes this way and he looks at its R value, and he comes this way and he looks at this R value. He does that for every possible move. He looks at what the board looks like if you make the move, he evaluates the board, and that gives you some evaluation of this action, right? And which action does he take? Well, being wise, he takes the action that leads to the highest expected reward, right? He goes to the state where the R value is the biggest, right? So there, it's the highest one is the R2, and so he moved over there, right? And now, given that we know that that's what the player is going to do, we know the player is going to move from state 1 to state 2, so we can define what value R1 should be, right? We can say R1 should be, what value should it have? It should have the value equal to the maximum of its neighbors, right? That's a rule, right? If you want to say what property should the R values have, well, one property they should have is that the R value of this node should equal, right? The R value of the current node should equal the maximum overall actions from out of the current node of the R value of the next node, right? Everybody kind of buy this as an equation that we should satisfy for the R values. Remember, because we were struggling where these R values came from. So we're just writing some properties we want of the R values, right? Does that make sense? All right. Now, let's see what would happen in practice if we did this, right? Here's a whole bunch of states, and suppose it's just this guy and he can get to the reward, right? What do we want him to do? We want him to walk to the reward, right? That's what we want him to do, because there's the reward. He's going to be happy if he walks to it, right? But what does it say here? Our rule says each value, the reward at each value is going to be the expected reward. And so that kind of labels all of these nodes with the same number 100, right? If each one, right, if this one's 100 and this is the maximum of its neighbors, so this guy will be 100, and this one's the maximum of its neighbors, so it's going to be 100, and suddenly all of them are labeled 100. And the problem with all these hundreds is which action the guy takes. All he does is he moves to the number, the state with the highest number, right? And they all have the same number, so he doesn't know which way to go, right? So that's a problem we need to fix. How do we want to fix it? Is we want that 100 10 years from now is not as good as 120 minutes from now, and it's certainly not as good as instant gratification. So we're going to have this 100 value decay as it gets further and further away from the actual reward, right? And now because it's delayed like that, since he moves towards the bigger numbers, that's going to get him moving in the right direction, right? Does that make sense? We want these numbers decayed so that he knows if he follows them, he goes in the right direction. And how do we manifest that? Well, this is our current number, and this is our next number. they're no longer equal, right? So we're going to just add a little decay in here. We're going to say, you take what value do you want our current node to be? Well, you take the maximum of your neighbors and you decay it by a little bit. You just multiply it by 1 minus 0.001, right? You multiply it by little something small, and that makes all our numbers decay like this. And it also makes sense because getting a reward sooner is better than getting it later, right? So the reward at your next step, you're going to get your reward sooner. Currently, it's going to be a longer delay to get your reward than later. So as you get closer and closer, right, your reward goes higher and higher because you're getting closer to the reward. Right? Does that make sense?
Yeah.
But Jeff,
and that's
here you're only talking. Here you're only talking about the robot nodes, right?
Yeah.
Because the other nodes
are different.
You don't want to do, won't do the maximum. And
yeah.
And if a robot, if you do what you say and you calculate back and you get a whole bunch of hundreds,
right?
Does it really matter which 100? Like all the hundreds mean you won the game.
No.
So why do you care?
No. No.
You might not know how to win the game, but all the hundreds say you won.
Oh, right. So if you get here, then you will win, but you don't know how to get there, right? Right. You don't get the 100 until you're here, right? So you don't want to be, right? So here he doesn't know which way to go.
Yeah, but in a classical game,
yeah,
you know you won. You just don't know
how to win. Yeah, exactly. Right. And if there was a time, right, in what we did before, there were layers. So you knew which way to travel, right? But now there might not be layers. So we're kind of adding this extra time dimension to tell you which way to go, right? All right, so now that was just for our robot's term. If it's his opponent's term, right, then again, he has actions, various actions that he could take. And each action, he knows how the board currently is, and he knows what actions he could take. And that moves you to a different board. And as Martin said, which action does he take? Well, he takes some move, which moves the board, right? So it's moving our robot because the robot says what state of the world he's in. And as the devil makes a move, it moves the robot to a different state of the board, right? And which state does he move us to? He takes the one that's the minimum of your neighbors, right? So what value should R2 be? Well, just like R1 was the maximum of its neighbors, R2 is going to be the minimum of its neighbors, except we're going to need to. So I must admit, I don't often read things. I usually just make them up myself. So I had to say, do I multiply this by 1 minus epsilon, or do I multiply it by 1 plus epsilon? And again, you can think, what does the adversary want you to do? He wants you to move away from the winning strategy, right? So that means he's going in the direction of the smallest number. So we want our weights to get smaller as we move away, because he wants to move in that direction. And so then you want to say, hey, this is my current node. He wants to move from the 99 node to the 98 node. So he oops, there's that one up there is a typo, but he's making the I thought it was a minus still. Maybe this one's a typo. Anyway, it's either a plus epsilon or a minus epsilon that we stuck in there. let's move on quickly because I think I didn't have it right. All right, so anyway, right, so I mean, what is it? This is his current node, and he wants, yeah, I guess it is a plus, right? Because he wants his current node to be slightly bigger than this next node. This is his current node, then this is his next node. So he wants his current node to be slightly bigger. So that's a plus, and that one up there should be a plus too, right? And it kind of makes sense because the opponent wants to take longer and longer to reach goals that are positive, right? Even if he can't win, he wants you to delay you from winning. So he wants to move you away from the winning spot. All right, everybody kind of follow those kind of states, right? So now we can do what we did with Markoff chains. We can say, well, in this state, the universe is rolling coins. And so there are various actions that it could take. He could take various actions. The universe is taking an action. Should it rain? Should it not rain? Should it snow? Right? Those are the actions that a random person should take, or you're playing Monopoly, roll dice. And then we don't know what the future will bring. So associated with each of these actions is the probability that it moves in a particular direction, right? So if in this state, it flips a coin, which says with probability P1, you go this way, probability P2, you go this way, and it takes some random walk, right? And so now, because we know what this node is doing, we can write down what the current value should be, right? It's the expected value, right, over all the various probabilities of the next node, right? So this is just the weighted sum of the R's neighbor. And because we don't need to delay the time here if we don't want, we can just keep that as a 1, right? Does that make sense? So now, oh, the halting state, all right? So if it's a halting state, the game has actually stopped. And so at this point, the machine gets rewarded. And so we know the R value, right? Here, the R value is determined by, because the game's over, right? So, right, everybody understands those R values, how we compute them? And so now in some ways, we have a big system of equations, right? We have the equations which tell you how each R value depends on the other R values. And we need to solve all of those equations, right? And so what's happening is each player has to choose which action to take, right? But which action he takes is based on, right? What does he do? He goes to the next. If it's my turn, I go to the state which maximizes my R value. So the action I take depends. And if it's his guy, he goes to the state with the minimum R, right? Either way, the action taken depends on the R values, right? And similarly, the R values, right, to dictate which actions the players are going to go, right? So it's a circular loop here, right? If we knew the actions everybody was going to take, then we would have a fixed set of equations which we could solve for the R values. But the actions they take dictate the R values, and the R values dictate which actions you're going to take, right? So that becomes a circular argument, right? Everybody buy that? So what we're going to do is maybe we'll start with random R values, and we update them, right? We update the actions based on our current R values, right? And then we update our R values based on our actions, and we go around and around and around, right? Now, it turns out you don't have to store the actions, you just have to store the R values, right? Because if you have R values, then the actions are determined. right? And the hope is that this all converges. I was looking for an image for converging, and I came up with this one because I imagine all the birds are converging onto the tree. But when I showed various people this picture, they didn't get that it was converging. But anyway, that's all the birds are converging onto the tree picture, right? So hopefully, if you keep doing this, updating, then it all converges to some nice R values, right? And when you have those R values, what happens with those R values? Well, they make every player play optimally, right? If these are the perfect God's given R values, and the white guy takes the max, and the red guy takes the min, then they're all playing optimally, right? So it does converge to the optimal way to play this game, right? And now, does it converge, right? Well, in this case, right, we started at the end and we bubbled backwards and it converges, right? I mean, you calculate the values backwards, right? So the advantage of this tree is it doesn't have cycles, right? It's a tree, all the time just goes forward. So you can calculate, right? You can calculate at the end of the game, what's the state? And then one step beyond the end, one step beyond the end, right? And you can bubble backwards and you can calculate all these R values, right? Are you puzzled, Martin?
Sorry, I just took a second to unmute.
Yeah.
But in the tree, like if it's a game that has cycles, like
right.
chess, two people can just keep
Cycle.
making the same moves back and forth. The game goes forever. Then the game tree, no, it doesn't have cycles, but it has an infinite depth.
Right. Sure, for sure. But we're going to, I guess the way we're representing it is each state just tells you where the pieces are, doesn't tell you what time it is, right? If you added in there what time it is, then it wouldn't have cycles, right? If you don't include what time it is, then it has cycles. But what I'm showing here in this picture is that you would learn if there were no cycles, if you added in a timestamp so you knew that the graph doesn't cycle, the game doesn't cycle, then it's well defined what the R values are coming backwards.
Yeah.
Right. And then our little frustrated guy is going to say, yeah, but they're cycles, right? So how do we deal with cycles? And right, because you could update this, and then you could go around and around and update things, right? And there's a theorem, and I'm sorry I don't know who proved the theorem, but Markoff chains are named after Markoff, so maybe he proved it. Somebody proved that what, right? So let's start with R values, some random R values. Well, I guess these finished nodes won't be random. There'll be hundreds. There'll be the finished unit. And let's just update the nodes one at a time, all right? So have some schedule. I'm going to update this number based on its neighbors, and I'm going to update this one based on its neighbors, and I'm going to update this one based on its neighbors. And you have some schedule in which you update them one at a time. And it doesn't matter what order you update them, right? The only requirement is that your schedule is long enough that each node is updated often, right? You update, maybe you just cycle through the nodes in some order. Everybody gets updated often, right? Then there's some theorem that says the R values will converge quite quickly to the correct values, even if they're cycles, right? And I certainly am not going to prove that because I have no idea how to prove it. All right, everybody good with that? So now there's another problem. And the other problem is we have way too many states, right? Remember, the number of placements of the board, of pieces on the board, is just huge. So we can't update each of these nodes because we can't look at each of them. There are way too many to update them all, right? So instead, that's where neural nets are going to come in, all right? And what do we do with our neural net, right? So what does our machine want to learn? He wants to learn a mapping from what? Given the placement of the pieces, given his current state, right? What he knows about the world, what does this neural net want to compute? It wants to compute the R value, right? It wants to know what that's ultimately, if you're learning how to play chess, ultimately what you have to learn is, given the current placement of pieces, is what probability am I going to win, right? And soon as you know that, then you're a perfect player. Why? Because given the current state, you try each way to move and you evaluate it. And if you can evaluate it correctly, then you go to the one that's maximum, right? So the whole learning of the game boils down to this: given my current state, evaluating how good that state is. All right. So that's what we want to learn. And how do we learn it? Well, the way we normally learn it is the supervisor knows the correct answers, right? And so given she knows the correct answer, given the current weight, she can calculate what answers your neural net is giving, and she can tell you how far you are from the current weights. And given that, our neural net, our robot updates his weights to get closer and closer to the current weights, right? So that sounds all great, except we don't know the right R values, right? The whole point is to learn the R values. So how can it learn to compute the R values when we don't know the R values, right? So instead, remember, we're going to have some schedule in which we update these nodes. So let's talk about how we're going to update the nodes. What we're assuming is we have R values everywhere already calculated, and we're trying to update the R node of this particular node, right? Does that make sense? And so let's look at all our neighbors, and they all have R values. So who computes? In order to update, before we can update this R value, we need to know the R values of our neighbors, right? So how do we compute the R values of our neighbors? Well, we have a machine down here that knows how to compute them, right? So this is saying our current sense of what these R values should be, right? So what we will do, our robot will compute all these next R values. How does it compute it? You give it the description of the board, and it will give you the R value of that next node, right? So we use our current machine, the current weights of our machine, to compute our neighbor's R values, right? Now, what value should be at this node? Well, the value that should be at the correct value, given we know the values of these nodes, the correct value at this node is according to this equation, right? So we can take the R values of our neighbors to compute what our new R values should be, right? And so it's like taking, that's what, before when we were updating them one at a time, we were taking the current values of these R values and updating this value using this equation. So now what we're doing is we know what the output should be here. So now what we do is now we have a supervisor who in some ways knows what the output's supposed to be. So how do we learn, right? We want to change this value from the white current R value to the purple current R value. And how do we change it? Is, well, the machine will say, oh, what do I compute it as, right? Given the placement of the pieces here, right? I can compute what I think the R value should be, right? That's the value that it thinks it is. And now, look at, we have two values. We have what our current machine thinks the R value is, and we have what our supervisor says the R value should be. So there's a difference between those, and that gives us an error. And what do we do with that error? We back propagate that error back, and we update the weights. Right? Does that make sense? So each step, you choose a node that you want to update. Now, do you completely update it? No, it's not going to move the white answer all the way to the purple answer in one step. Maybe we learn maybe we do a couple passes here to update, right? We do a couple passes here. We figure out how to update the weights so that this, as we update the weights, this white answer is going to come closer and closer to the purple answer, right? So we do that for a while, and maybe we don't have to get all the way until it's perfect. And then we go to another node, and we do it at that node, right? And so you keep going from node to node to node, and as you do it, you adjust the weights. And hopefully then if you keep doing it, it converges to computing the right answer. Right? Does that make sense? Now, then you could ask, well, what order should I update these nodes? And the thing is that that's a huge graph. There's so many states. You never want to update nodes that you're never going to get to, right? There are positions. I heard that if you gave an expert chess player the positions of pieces in a real game, right, he can understand it really quickly. But if you give him pieces that are in a random position, he just doesn't know how to understand them, right? So we don't want to update nodes, states of board positions that the game's never going to get to. So instead, what you can do is you can start from the beginning with an empty board or with the chess pieces in the start state, and you play a game. And since the R values are random, you're doing it's a random game, right? But at the end, somebody wins. And so then as people win, these R values here will slowly trickle back and get updated. And hopefully it all converges. And that's how you win Go. And that's all I know about it. All right, how are people doing?
All right. I'm in the dark here.
Jeff, I have a question on that.
All right, Daniel.
Yes, maybe you start to get those states, you start with games that are almost over, because then the number of states to get to the goal is trackable. In other words, so you take some real games, and then the last 10 moves or the last 5 moves, wherever you want to start, you start from there and start assigning weights. Is that a strategy that's been used?
Yeah, so I would say absolutely yes. And if you come back way to the beginning here, when they first got AlphaGo to win, they say it played by watching other humans, right? So they had, what they had laid out is billions, I don't know how many games that humans have played, and then it could go back. It could say of all in positions that the games were at, how were they evaluated, and then it could move backwards throughout all the games, right? So if I had a lot of games and I wanted to learn from them, I would do it exactly what you were saying, is I would start at the end of the game and sort of say, well, who won in each of those games? And then go backwards through each of those games and propagate that information backwards till you got to the beginning of the game, right? But I think if you didn't have any humans, any games at all, then could you say what an end game looks like? So you might have to start at the beginning forward to know what an end game looks like. And as I said, later they started with just the rules of Go. So they would have had no idea what an end game looked like to play backwards from. So I think they had to start at the beginning. And as you start at the beginning, right? I would say, this is just my making it up. Don't quote me on this, right? You play all the way through, and then given that game, you can propagate that information just a little bit backwards, right? So as we play through, it's random because we have random R values. We're doing random moves. And then a little information gets propagated back. And then you go all the way through a new game and a little information gets back. So you probably have to play a lot of games before anything reasonable propagates all the way to the beginning. That's my guess.
You're talking about starting at the end of the game or the beginning of the game,
right?
And say you're starting at the beginning of the game, and you say you're playing forward, but really you're not necessarily playing. What you're doing is you're choosing what nodes you want to calculate your R value on. And so are you suggesting that you would start with the board at the beginning and calculate the R value of all the opening moves?
No, because because you can't calculate. I mean, we just have random. I would say we start with random R values in the states, or maybe all neutral R values, 0, and then as you move forward, I would start. I don't want to. I guess there's just so many states. My thinking is I would never want to go to a board configuration that isn't going to arise from some game, because that's going to waste my time.
Yeah.
So I start in the configuration where it's the beginning, and then initially everybody is making basically a random move, right? Because they have no information. So you're taking one path through this state space as people make random moves, and then somebody wins. And then we learn that state space, that board configuration that we got to by playing random, we learn who won. And that trickles some information into our neural net, right? And then we start at the beginning again, and we follow it's more or less a random game at the beginning, but maybe we get to the end and we get we're at another end game, and we learn information about who won, and that trickles some information into our neural net. And as you keep doing that, it trickles more and more information into your neural net. At first, it's just learning about what end games look like, but it's looking at what does an end game look like that you get to when you play randomly. And so if you keep doing that, what it learns is random end games, who wins, right? And now, after you've really learned what who wins a random end game, then when we get just before the end game, we know how to play, right? And we learn how to play the 1- end game, right? And that trickles back, right? And I think it would then keep trickling back until you got to the beginning and knowing what your first move should be.
Yeah. Okay, so you start with the beginning of the board, you take a random move,
right? And
you look at that state and recalculate the R value for that state.
No, but you can't. No, Well, you could try to yeah, that's true. After you've been playing in a while, you have R values that mean something, mean a little bit. And so then as you move through, you could calculate the R values, right? Or maybe what it does, I don't actually know, maybe it plays the game all the way forward and then it goes backwards calculating R values. I think that would make a little bit more sense to me.
Yeah, okay, because it's only when you calculate R values that you're doing any improvement.
Yeah,
Otherwise,
exactly.
you're just walking through a random game.
Yeah. So I think that's what I'm going to state. And of course, I'm making this up. I would play a game randomly all the way to the end, and then I would propagate R values back and hopefully that's meaningful, right? And then I would play another game, and I would propagate that R value back. And you do that a billion times. And then they win. Right? We definitely have proof of concept, right?
Great. Yeah, thanks.
Any other thoughts? I think this is supposed to be an hour, right? So I think we ran out of time.
I think so. I have one idea.
Uh-huh.
And it's about, maybe this relates back to what you were talking about earlier with language.
Uh-huh.
So like this idea of like translation, looking for the right word if you're going from English to French.
Right.
And so many possible ways of constructing the same phrase. So it's like having a giant thesaurus or a dictionary, right? And the right words have to be picked out and assembled. It's kind of the structure, learning the structure, I guess it would be in language similar to this game tree, right? Finding the right solution.
Right.
I got that?
Yeah.
Okay.
Yeah, sounds good. Sounds good.
It's all very philosophical sound.
Yeah, well, as I think I said at the very first moment, I find all this stuff oddly spiritual because, why does it work? And how does that explain why we're here? Right? How did we learn to walk?
Think.
To think, to have language, to do anything, right? It's,
yeah.
If you're believing in evolution, then this all had to happen somehow, right?
Thanks, Jeff. I'm just looking at the chat. I don't see any questions. So
no, there's only 3 things there. Thank you. We got to thank you. And all right.
Awesome.
All right. So that was fun. And they may schedule events again for next. I don't have a place to register for next time. This webpage, this Zoom call is the one I teach on. You can come to this Zoom time any time and see if I'm teaching. And so we might use this again next week or who knows.
I'm not sure exactly. Today, unfortunately, we had a conflict with another event, and that's why we had to use. And thank you so much for letting us do that.
Yeah. All right. So Nadia, somehow we can. Are the other events scheduled yet? Could we find them?
Absolutely, yes. So let me. I think I should have the link for the other ones as well. So link meaning link for the registration.
Right.
The Zoom links normally we sent out in the morning of the event.
All right.
But the registration links, yes, that should be up and running. Let me forward that to you, Jeff.
All right. If you email to me, then I will put them on my little page, and then people can find them there or with you.
Awesome. Thank you. Appreciate that.
All right, everybody. Have a great week, and I look forward to seeing you again. And thanks for coming.
Thank you.
Thanks a lot, everybody. Take care.
Thank you.
Thank you
Bye-bye.
very much.
Bye-bye.
Excellent class. Bye-bye.
Hey, Jake.
Hi. I'm just leaving.